Okay, welcome back. So before we resume, let me make some quick announcements. So the first one is about the social dinner. We are going to have a social dinner on Thursday, which will take place in Terra Brasilis in Urca. You should have received an email about it with more details, and then we just please ask you that you confirm following the instructions on the email by tomorrow afternoon. So the second announcement is about a slight change in schedule for the presentation by young researchers. So today at 4 p.m. We will have a talk by Ageu Barbosa Freire, while on Tuesday at the same time we are going to have the talk by Rafael Ferreira Holanda. And finally, final announcement that in the end of the scientific activities of today, we are going to have some welcoming words, and then we are going to have a cocktail. So I guess this is it for the announcements. And now it's my great pleasure to introduce our next speaker, Paolo Cascini from Imperial College. Paolo has made great contributions both to birational geometry and the theory of foliations. And today he's going to explain to us some connections, and he's going to talk about minimal models for foliated varieties. Please, Paolo.
Thank you for a very nice introduction. Thank you for giving me the opportunity to be here. Of course, I'm very happy to be back here. Okay, so I'm going to talk about, I'll try to make my talk not terrible, but probably will be a little bit terrible towards the end. And to this end, I will talk about motivation. So I'll try to motivate what we're doing, although the motivation have almost nothing to do with what I'm going to talk about. It's just to give some idea. So this is working, everything that all the results that I'm going to talk about are in collaboration with Callum Spicer from London, from King's College. And everything that I'm going to talk about, it's only over the complex numbers. So this is the plan. I will give some motivation. I will talk about what we mean by a minimal model for foliation. And then I will talk about some of the results, like sometimes flops exist, sometimes flops don't exist, and why we care about this. Okay, so let me start with the introduction. So what is a foliation? I suppose here foliations are common knowledge, but let me remind you what a foliation is on a complex projective variety. So we fix the complex projective variety of dimension n, and we say that a foliation is a coherent subsheaf of the tangent sheaf, which satisfy two very, very standard properties. The first property is that it's closed under Lie brackets, whatever it means. And then the quotient between the tangent sheaf and the sheaf defining the foliation is torsion-free. So I will explain, although it's probably clear, why the first assumption is needed. But before we do that, let me start with an example. So this is the example that I personally always keep in mind. This is one of the reasons why I'm interested in foliations. My background is in birational geometry, so I like fibrations. And fibration appears all the time. So in particular, any fibration will define a foliation. So what is a fibration? For me, a fibration would be just a surjective morphism between two normal varieties, which has connected fiber. So using algebraic geometry, we just say that the push forward the structure sheaf of X is equal to the structure sheaf of Z. But all it means is that all the fibers are connected. So an example of foliation is just given by looking at the kernel, the differential map of the fibration. So this is natural, will satisfy, it's a very simple foliation from many point of view. And the natural satisfy the property of being closed under Lie bracket. So these foliations will not play much of a role in this talk, but they're called algebraically integrable foliation. So whenever I think of foliation, the first example I personally think about is this one here. And actually, one good thing about foliation is that they're very flexible. Whenever you have a foliation on one variety, and you have some kind of map from one to the other, then it's easy to induce the foliation, which is not true for fibration, right? If you have a fibration, it's not true that even if you have another birational, if you have a birational map, it's not true that the fibration is induced. But foliation is true. And why? So suppose that we have a foliation f on x, and suppose that you have a dominant map from y to x, then we can always induce in a very natural way a foliation on y. So how do we do that? Well, it's very similar to what we did before, except for the fact that, okay, what I wrote here is not very precise. We need to restrict, we need to restrict to the locus where phi is well defined, but that's okay because we can extend the foliation after that. So assuming for a moment that phi is defined everywhere, what I do is to just look at the kernel of the composition of these two maps. If phi is not defined everywhere, we just work where the phi is defined, and then we take the extension of the foliation. So in particular, and this is going to be very important for us later on, if you have a foliation x, and you have y, which is birational to x, it can be a blow-up or the inverse of a blow-up, whatever, really, it doesn't matter because phi does not need to be defined everywhere. Then you automatically have a foliation on y. So having a foliation, it's a birational invariant in some sense, which is going to be very important for us later on. Okay, so again, we try many ways to imitate what happened in the classical algebraic geometry, in the classic birational geometry. So what we want to study, and this is very, very standard, is the canonical sheaf, or sorry, the canonical divisor of the foliation, which is defined exactly in the same way that the canonical divisor of a variety is defined. So whenever we take the determinant, so the highest wedge power of the dual of the sheaf define the foliation, and this is a rank 1 sheaf, of course. So we take any divisor which defines this rank 1 sheaf, and this is called the canonical divisor of the foliation. So it's not unique, but it's unique up to equivalence, linear equivalence. So exactly for the canonical divisor. So the minimum of the program for varieties asks us, how can we make kx nice? And the minimum of the program for foliation is exactly the same, is how do we make kf nice? I mean, the canonical divisor of the foliation nice. Okay, so one standard definition. So I'm going to, again, be sloppy here. I'm going to assume that x is smooth, because it doesn't really matter to me later on. So I've defined the singular locus of the foliation to be the locus where the normal sheaf, so the quotient between the tangent sheaf and the sheaf defining the foliation, is not locally free. So this does not work quite well if x is singular, but for what I'm going to say next, it's OK. So Frobenius theorem, this is a classic result, explains why we need the foliation to be closed under the bracket. Because if you want to make sure that there are things called leaves, meaning that we have locally a fibration, that the foliation is defined locally by fibration, then we want to make sure that the foliation is not just a distribution, but it's closed under the bracket. So the theorem says that if you remove the singular locus of x and the singular locus of f, then at any point, locally and analytically, the foliation looks like what I defined before. So it defines by holomorphic map from x to the Euclidean space n c to the n to the minus r, where n is the dimension of x and r is the rank of the foliation, and everything else is the same as before, except the fact that it's not algebraic, it's not defined everywhere, but it's only defined locally and analytically around x. Okay, so this is why foliation, why we care about foliation. And the leaf is something that locally looks like a fiber of this map. I'm not going to, these things will not appear very often. I just wanted to give a standard definition that appear on foliations. Okay, very good. So I'm going to start with motivations. As I said, I know almost nothing about moduli spaces. I never really work actively on moduli spaces. But of course, that's the main goal for any birational geometry, I think. You can ask, what does it mean to classify varieties, like even curves? What does it mean to classify curves? So each of us can have a different answer, but probably the standard one is to say, we want to construct a moduli space. If you know the moduli space well enough, then you have an idea what the classification looks like. So this is our goal for foliation. So somehow, this is a very, very open problem for foliations. We want to construct some form of moduli space for there's a type of moduli spaces of foliations. So what is the moduli space? Well, okay, I just recall what we know. For instance, for curves of genus greater or equal than 2. We know that from long time that we have a moduli space of curves. This was due to the Lim-Mumford, I think, and the way it was constructed is by using GIT. So again, knowing MG is pretty much having a good understanding how curves behave. Now, the question is, can we generalize this to higher dimensional varieties? And the answer is not quite, meaning that GIT doesn't work quite well to construct moduli spaces. What we need to do is to be a little bit more carefully, to work a little bit more carefully. And this was handled by several people, but I think the first two people that really work on this, actually 3 people that really work on this are Kolesh, Fabaro, and Alexeyev. So what they did is that instead of working with GIT, they say, okay, why not we use the program, Bayesian geometry, to understand the moduli space? And they will try to explain why. So if we just take minimal surface of general type, so this means that the canonical device is big enough. So canonical device of big enough, enough means that it's non-negative on every curve. Big means that it has a lot of sections. So just the equivalent of having genus greater or equal than 2 of curves, pretty much. And most of the curves are of general type, so most of the varieties are of general type. Actually, almost every one is of general type. So even this space, which is supposed to be very nice, is not separated. And the reason why it's not separated is because there are flops. So in other words, you could have 2 mirror models that are connected somehow, but they're both limit of some curves inside the moduli spaces. So we cannot work with this object here. So what was done by Kolesh, Fabaro, and actually I should say Alexeyev, is to construct a modular space with ample canonical divisor by using the Miranda program in dimension 3. So this works. If we, instead of working with big and F, we work with ample, there is a huge, huge difference. And I think that philosophically the difference is because the canonical model, which means the variety for which the canonical device is ample, it's unique. It's the proj of something. So there's only one canonical model, so it's good to represent these objects. Okay, so the good news is that we can always do that. So thanks to the MMP, which we know to work, we know that for any smooth complex projective variety, there exists a Mia model and a canonical model. So Mia model means that we have a variety which is Bayesian to X, where the canonical device is F. So in other words, we can think of it to be non-negative. It's positive it's non-negative on every curve. And then we have sorry, I'm not used to look behind, a canonical model where the canonical device is ample. Okay, so the canonical model, as I said before, it's always unique because it's isomorphic to the proj of the ring of section of Kx. I'm not going to explain what it is because it's not going to play a role. But the idea is that this ring is finitely generated, whatever it is, and so this model exists. And it's unique because it's uniquely determined by this guy. This guy is for smooth variety, it's a Bayesian invariant. On the other hand, minimum models are not unique in general. It's very, very easy to find examples. And the result of Kamamata says that even though they're not unique, any 2 minimum models are connected by flops. So they are very standard operation. I will talk a little bit about it later, that connect any 2 minimum models. So somehow, let's forget about moduli spaces. My goal is to try to understand, or our goal was to try to understand what happens to these 3 lines for foliations. Can we try to have Mia models, canonical models, and flops somehow? I mean, once we have Mia models, can we try to see how they're connected by flops? Okay, any questions? So I'm going to talk about Mia model program for foliation now. I'm not going to say much about what the Mia model program is. I'm just going to skip the usual details. I'm just going to say the end result. So there are many, no, I'm going to talk about this first. So there are many people working on the modular space of foliation. So again, I'm not one of them. I'm just interested in some of the ingredients. And the reason is because there are many, many problems when we try to work on the modular space. So for instance, one is boundedness and so on. I'm at the moment only interested about separateness, which is somehow related with flops. So yeah, so there are many people involved. And again, we want to try to imitate what we did for varieties. So we want to find some kind of Mia model and canonical model for foliation. I think this is what I said before. Okay, so there are some good news and some bad news. The good news is that if we work on a surface, and if we work on a foliation, such that, like before, we assume that the singular, okay, I'm going to skip some details. I'm not going to talk too much about singularities. So canonical singularity is the equivalent, and the definition is exactly the same, of canonical singularity for varieties. So there are some singularities that appear in Brownian geometry, and we just take it as a black box. Smooth varieties are not enough, or smooth foliations are not enough. So we just make the class larger. So please forget about, if you don't know what it means, if I tell you the definition, I don't think it will help. So please forget about this word canonical singularities. Yeah, I will do it now. That's exactly the definition, yes. Sorry?
Canonical singularities are on X.
Both X and Y, yeah, at the end, yeah. Sorry, not on the variety X, but on the foliation. So the foliation must have singularity which are under control, yes. So we assume that KF is big. So again, it means that he has a lot of section, whatever it means. So in this case, actually, much less is required. We just need to be set effective. But again, I'm trying to be as little technical as possible. Then there exists a Mina model. So what is a Mina model? So there exists a Brownian morphism. Okay, I forgot to say Mina model means X to Y, it's a Brownian morphism. So exactly like in the case of surfaces, in which, remember, whenever you have a foliation on X, automatically you have a foliation on Y. So what we require is that the corresponding foliation on Y has NF canonical divisor. So this is a Mina model. Okay, so it's exactly like what we expect. And this guy exists. For surfaces, this was proven many years ago that this always exists. Okay, so this problem has been solved, so it's good. But on the other hand, canonical models don't exist. So there exist foliations with the canonical divisor, which is big enough. Actually, there are several kinds of examples, but this is what I care about at the moment. There's foliation with KF big enough, but not semi-ample, which means that you cannot, first of all, you cannot construct the canonical model of K. You cannot make a KF ample. You cannot just take another Brownian morphism. Instead of X to Y, you make it even more, you contract even more curves. But this doesn't work. You cannot make KF ample. Another way to say is that the ring is not finitely generated. But it turns out that this is not a huge, huge problem, because in this, we know all the examples, thanks to McQuillan, we know all the examples where this happens. And in all these examples, we can contract the bad locus. We can contract all the curves such that Kf times C is equal to 0. So Z is not quite the canonical model because it's not true that Kf Z is ample. But from many points of view, it's good enough. In other words, what happens is that on some curves, it could be non-torsion. Degree 0, but non-torsion, something like that. Okay, so there is no canonical model, but we're not very, very far away from it. This only for surfaces, yes. All these, all these pages for surfaces, yes. Yeah, my point is to go to threefold in the next slide, I think. Thanks, yes. Okay, so now it's threefolds, and that's all pretty much I'm going to say. I'm going to stop at threefolds. Okay, so let's suppose now what happens next. We want to understand what happened for dimension 3. So even if you want to work on the moduli space of surfaces, you need to work on MMP in threefolds. So we need to understand what happens in dimension 3. So let's suppose we have a foliation, again, with nice singularities, and rank R. So R must be either 1 or 2, unless you have trivial example. And again, we assume that Kf is big. So what we proved for rank, this was a few years ago, for rank equal to true and rank equal to 1. So for rank equal to 2, it's my result with Callum. For rank equal to 1, Mike and McQuillan got some results, and then we got the full results in full generality. We showed that there exists always a Brownian map, in this case, in such a way that KFY is an F. So it's not anymore a proper map morphism, it's not a regular morphism, but it's as good as a Mina model. I mean, it's exactly what a Mina model is, okay? So yes, so whatever we want it to be true is true. And phi, it's obtained if you know what it is. If you don't know, it doesn't matter. Phi, it's a sequence exactly like in the Mina model program of divisorial contraction and flips. So we know what happens between X and Y. There are elementary transformations exactly like in Morris' program. Okay, so this is done. Then actually, this is just off topic, the same is true for algebraic integrable foliation. So it doesn't matter what the dimension is, we can prove that flip exists for any dimension, any rank, assuming termination of flips. So I'm not going to talk about this, so I will not spend much time on this. Okay, so now we go to the point of this. So what I'm going to talk about is some results about flops, what happens for flops, or what happens to mirror models in dimension 3 for foliation of rank 1 and rank 2. So I'm going to start with rank 2. The picture is completely different between rank 1 and rank 2, we'll see. So I'm going to start with rank 2. So we assume that we are working on a normal complex variety of dimension 3, and F is a foliation of rank 2 with canonical singularities. So in this case, flop exists. So maybe I will explain what a flop is. So we assume that we have a foliation X and a morphism from X to Z such that, okay, so this morphism has the property that on every curve, so this is a Barashian morphism, actually small. So small means that the locus where is not an isomorphism, so the exceptional locus of F, has codimension greater or equal than 2. So since we're in a threefold, it means that it's a curve. Okay, cannot be points, so it must be a curve. And the property about this morphism here is that for any curve which is contracted, so such that kf times c is equal to 0 for any curve c which is contracted. Okay, so this is what can happen if you have, so for instance, what you can think about is that this is the mirror model, and this is the canonical model, and you want to understand what happened to this morphism. Okay, so in this case, we show that, with the X assumption that is written there, the relative Picard number is equal to 1. So in this case, the flop does exist. So what is the flop? So the flop is a Barashian morphism, which is an isomorphism on dimension 1. So I didn't know how to do the diagram there, so that's why I do it here. So we get another map, another morphism from X prime to Z. So this is again small. So the exceptional locus is a curve. And it has the same property that what is written here. So there's a foliation F prime on X prime. So F prime is just equal to the induced foliation on X prime, which is still has the property that this is true. Also, this is true. But why is it not an isomorphism? Well, the idea is that, okay, what does it mean that the relative number is equal to 1? The idea is that whatever is positive here becomes negative here. So, in other words, if D it's F ample, so in other words, it's positive on every curve such T, then the corresponding divisor on X prime, so this one I should correctify, it's anti-ample, and vice versa. Otherwise, it would be just an isomorphism, okay? So again, this object here appears all the time in many different fields, but in particular when we try to understand how two mirror models are connected. So in this case, the flop does exist. So this is the good news. Actually, my student, former student of mine now is a student of Kalogirus, and then my student Pascal Voigtle, so Dongchenjia and Voigtle, proved that exactly the same result as, or at least this is a work in progress, but I think that is very close. The same result as Kawamata holds in this case. So if you have two mirror models, so suppose that we start with any foliation on X, and we have two mirror models, then the two mirror models are connected by flops. So, Y1. So we have two different mirror models. And then the corresponding map here, which is always well defined because it's a Barashian map, it's a composition of flops. So that's why we like flops. Okay, so again, in this case, the picture is as good as what we have for varieties, at least in terms of mirror models. we don't know, and actually it's not the case that the minimum model is unique, but we know how they behave in different models. So we'll talk a little bit about the proof later on, about theorem 1. But let me continue and say some results in rank 1. Okay, so in rank 1, the situation is completely different. What we prove is that we can find a foliation of rank 1 and exactly the same picture as this, but where, I mean, on the left-hand side, where the right-hand side does not exist. Okay, so the picture is much worse than, and this looks like a bad news, but there is a caveat later on, so it's not too bad. But there is something even worse than this, actually. So what is worse is that even worse than what Michael McQuillan proved happens for threefolds. So for threefolds, I remind you, what Michael proved is that even though there is no canonical model, we can still contract all the curves on which kf is equal to 0. But in threefolds, this does not happen, meaning that we can find, so this picture is much worse. So in other words, we can find a foliation on X such that kf is big enough, but there is no way to contract the exceptional locus, the set of curves on kf, over which kf is 0. So this does not exist. Even assuming that Z is an algebraic space, such that kf times C is equal to 0, if and only if the corresponding map is contracting C. So a canonical model will do this. A canonical model will do much more than this, because a canonical model will say, OK, the guy here is ample, but even the main ingredient is not true. So maybe let me just say one word about the proof. So the idea was we have lots of bad examples in surfaces. So we use Michael's example to extend them to threefolds. And the way we do it is that for each of these two cases, we construct a P1 bundle, which has a section. Okay, so the section will have the foliation induced by the base. And then what we do, which I've never seen before, I'm sure there's someone working on it, but I've never seen it. Maybe the expert here will tell me. I've never seen anything written down about this, how to extend a foliation to the threefold. So the way we do it is by hands. Given the section on the surface, we extend it to the threefold. And then we show that whatever we want to be true, to be false, is false with this example. Sorry?
You do the extension by what?
So let me write it down. So we have a surface Z with a foliation, maybe let me call it G, which is bad. And whatever bad means. And these are the example by Michael. And then what we do is to construct X to be the projective bundle of, so the P1 bundle associated to a rank 2 vector bundle, which is very simple, over Z. And we take a section here. So of course, there's a foliation G on Z0. So we pretend that Z0 is same as Z. I mean, we pretend, this is an isomorphism, so just to replace G. So what we do is to extend the foliation as a rank 1 foliation on X. Maybe it's been done, I don't know, but that's what we construct by hand. I mean, for this particular example, not in general. For this particular vector bundle, we extend the foliation. OK, so let's see. So yes, this is the explanation that I mentioned before. It's what is written there with different letters. So we can now find any morphism such that it contracts all the curves such that kf is equal to 0. All right. So as I mentioned, this is bad news. Well, actually, the good news is that it doesn't matter. Why? So because what we prove, all these theorems is in collaboration with Callum, sorry, with Spicer. So what we prove is that even though there are no flops, it doesn't matter because this does never happen. Why? Because the minimum model is always unique. This is, again, very unique about rank 1 foliation on a threefold. It does not happen for rank 2 foliation. So what we prove is that if you have a foliation of rank 1 on a threefold with canonical singularity, actually we prove it in any dimension, but I'm not sure if it's correct. So in dimension 3, I'm pretty sure it's correct. So assuming that kf is big, any two minimum models not only it's connected by flops, but actually they're connected by an isomorphism. So in this case, this is replaced by an isomorphism. Okay, and the proof is not very different from the proof that I'm going to talk about over the next few minutes for theorem 1. Okay, so we study locally what happens.
Are you saying that flops are isomorphic for the...
I mean, no, flops is never isomorphism by definition because we always say this one. So in our definition of flop cannot be an isomorphism because of this. But yes, so the equivalent of flop would be an isomorphism, yes. So there is no problem, even though there is no, so why do we care about this? Because again, philosophically, we would like to construct a moduli space, but there is no canonical model, so we cannot do that. I mean, theorem 2 tells us there is no way to hope for a canonical model. On the other hand, and then again, we are very, very early in this picture, so I'm not sure if this will give us anything, but what we show is that even though there is no canonical model, and even though there are no flops, the Miranda model is unique. So from many points of view, the Miranda model is as good as a canonical model. So it doesn't look too bad, even though bad things happen. Yeah, so the Miranda model is unique. Okay, very good. So now it's going to be the terrible part. And I'm going to talk a little bit about what we use in the proof. So, okay, so I will use some words that I'm not sure they're clear. I'll try to explain. I'm a little bit early, so I'll try to explain some of these ingredients. So I would like to introduce some of the steps that we use to prove existence of flops. So this is the same theorem that I mentioned a few slides ago. Okay, so first of all, okay, and this is the first technical word, FDLT, and also log canonical center. So there are two weird words that appear, but it doesn't matter. So by the work of some people, I mean, including Cano, which talk about resolution of singularities for Foliation rank 2 on a threefold, and then some work of Spicer, and then some work with Spicer and myself, it's possible to show that the foliation admits something like a resolution. It's not a resolution of singularities, but something like a resolution of singularities which behaves well. So what does it mean that it behaves well? So this is the technical language. If you want something precise, any log canonical center are simple. Probably means nothing. But what I can say is that the log canonical center are the worst possible singularities that appear in our foliations. So log canonical center, it's where discrepancy 0 appears. So just think of it to be the worst singularities that appear. And simple singularities, for our foliations. I'm not going to write the definition of simple, but simple means that we know exactly what the equations are, locally and analytically. So although these are the worst, simple means that the local equation of the foliation, so for instance, of the one form that defines the foliation, local equation of the foliation, are unknown. There might be more singularities, but the other singularities are better than log canonical centers. Okay, so this is the Algebraic geometry point of view. Okay, so what do we do that? Okay, so let's just suppose now for a moment that this morphism here, from x to z, only contracts one irreducible curve, which is smooth. It's a bunch of curves. It could be a bunch of curves, but I'm assuming it's just, for the sake of simplicity, I'm assuming that it's just one curve. Okay? So now, one of the difficulties in working in this field is that we cannot just work over a neighborhood of the curve. We need to work over a formal neighborhood. And the reason is because Frobenius theorem, more or less, meaning that we cannot find the surfaces which are invariant with respect to the foliation over which are algebraic. So what we do, and this is a classic, is to restrict on a formal neighborhood of this curve C. And we look at all the possible separatrices. which contains C. So separatrix means it's the equivalent of a leaf, although it could be singular, but it's the equivalent. At the generic point, it's a leaf, which contains C. Okay, now, it looks like a small detail to show that the sum of the SI is Q-Cartier, because you could say, okay, why not we start with something which is Q factorial? But that's not the case, because again, once you restrict from a algebraic variety to an analytic variety, Q factoriality is lost. So that's not given for granted. Whatever you assume about X, there is no way to assume anything about a formal neighborhood of this curve. So we really use foliation to show that this is true. And such that I will explain why this is important. The sum of all these surfaces times C is greater or equal than 0. Of course, if it was not Q-Cartier, this wouldn't make any sense. So this is one possibility. The second possibility, it could be both of them to be true. It doesn't matter. At least one must be true. The second possibility is that we can find one of these worst singularity, which is a zero-dimensional singularity, on this point here, which is a point here. Okay, both of them are good. We'll see that both of them, these cases, are good for us. Okay. Okay, I'm almost done. So to prove this, we use a Camacho-Sad formula, which we took from George, one of George's papers. Actually, what George, I think, is going to talk about on Friday. So this is the main ingredient of the proof. We use this fact here. It's hidden somewhere that we know the equation of C, and more locally analytically, and then we use something like that. I mean, we distinguish the two cases, the logarithmic case and Sado case, and then we work on this case, on this formula. Okay, so what do we do now? So we have this bunch of surfaces, and we distinguish these two cases. Now, by using adjunction, it's possible to show that this guy here, not only it's a flop with respect to KF, so not only this property is true, but actually this follows from adjunction, so it's not too bad. Actually, what we can say is that this is, I'm cheating because it's not Kx, but it's X is being replaced by a formal neighborhood of X. So X now is the formal neighborhood of X. But besides this technical part, this is not anymore a flop with respect of Kf, but now it's a flop with respect of Kx plus sum of Si. Now, we're not done yet. It's not true that these things exist. There are examples of flops, even in the log canonical world. So this is log canonical, whatever it means, which do not, I mean, one could say, okay, why not just use standard MMP? Well, there are flopping contraction for log canonical stuff which do not exist. This is an example, I think due to Fujino, but it's pretty much a folklore statement, that log canonical flips exist, but log canonical flops do not always exist. So we cannot stop here. We need to do something more. But if we know that the sum of Si times C is greater or equal than 0, then we can remove a little bit, and it will be a flip. Why? So what does it mean, a flip? It means that instead of having something times C equal to 0, you have something times C negative. Why? Because we remove a little bit of these surfaces. We know that these surfaces intersect C greater or equal than 0. And sorry, maybe it's not only a flip. It could be a flippy contraction or a floppy contraction. It could be that it's still 0 if you're unlucky and this number is equal to 0. So there's a small typo there. But the good news is that now it's not anymore log canonical. It's KLT. And for KLT flops, we know that they exist, or KLT flips, we're not sure they exist. So we know that using standard Bayesian geometry, this guy exists. There is a price to pay. It's not quite true that the standard Bayesian geometry tells us that flip exists in the formal scheme world. Actually, formal schemes, the minimum of the program is still very, very open. So this is something we prove in this particular case. So we can really use, there's something hidden here, which is very technical, that flips and flops in the standard minimum of the program work even if we don't work with algebraic varieties, but we work with formal schemes. Okay. Okay, so what about the second case? Let's suppose now that we are in the second case. Let's suppose that we have this point here, which is bad. It's a zero-dimensional point, which is bad. But now the point is that we know that the bad singularities are not too bad, right? We know the singularities for the bad singularities. So in particular, we know that there exist 3 separatrices, and one of them, in this particular case, there must be one separatrix, one invariant surface, which is transverse to the curve. In general, the separatrices could be all contained in C. But if you have such a bad guy, at least formally in a neighborhood of the point, then there is such a surface. Okay, so there exists a separatrix as transverse to C, and I forgot to write passing through P. So this is the point P. But then, well, actually, it's not going to be important for what I'm going to say next. But this is how this surface is. We know the equation. We can find this surface here in a formal neighborhood. OK, but now we do the same game as before. Instead of removing, oops, I forgot some SI there. So instead, so let me write it there somewhere. So instead of working with what we wanted to work, we work with this guy here. So this is what I wanted to say. Where all these are any other separatrice containing P. And all these separatrices must contain the curve C by this local description. Okay? So what is the advantage of doing that? Well, again, I had something which was equal to 0. Now this surface meets the curve positively. So I remove it, it becomes a negative number. So this number here becomes negative. And we know that flipper always exists. And so we're done. So sorry, I took 1 minute extra, but thank you very much.